So, we will take an example of a remote heat sink in this module, and there are many situations, as we talked about previously, that in electronic systems there may not be, for example, a laptop, there may not be enough space to mount a heat sink on top of where the heat is being generated. So, often what happens is to move the heat to a different location and mount a heat sink and a fan where there is enough space to do so. Um, in laptops, usually the current day systems are, for example, they use heat pipes, and in some occasions they use the heat pipe to conduct the heat to the back of your monitor, where there is a metal plate or metal body. The heat is dissipated using the hinges, it is called thermal hinges, and the heat pipe dissipates the or carries the heat from where the heat is generated under your keyboard to the back of your monitor, where it can where there is a large surface area to dissipate heat by natural convection. Or if the power of the laptop is much higher, then one mounts a fan and a small heat sink, and there is a vent in a laptop, so the heat pipe carries the heat from the heat source to closer to the venting location, where there is a heat sink and a fan mounted to dissipate heat. And typically those locations are have enough space to mount a fan and a heat sink. So, in this problem that we will consider is another case where you have a heat source on a PCB. The green slab is a PCB, and it is mounted with number of heat sources on the top. In addition to the heat source on the top, there is another heat source on the bottom, and the heat but the space for flowing air in the bottom is so limited, it is close to 1 mm or close to 5 mm or something, and that is not sufficient to dissipate the heat. So, the solution that is designed is to carry that heat to a location where one can mount a heat sink, that is on the top, where there is a large airflow happening from right to left, and to dissipate that heat off. So, we look into, since we discussed about heat pipes briefly in one module, we will see the benefit of having heat pipe in this example. First, we look into having copper rod as a means to carry heat from where the heat is generated at the bottom of the heat source to the top where the heat sink is called out. And so, this heat needs to be carried for over a distance of 150 mm, and you will find that the calculations that one has to do, which is L by Ka, a thermal resistance network that needs to be applied here. And we will see that the top side, because this heat sink is mounted at the far end of the domain, that the heat sink has to, the ambient air that is going to enter into the heat sink will be much higher than the inlet to the system itself, because all the heat dissipated by those heat sources on the top will be dumped into the flowing medium. So, if you calculate that, and as an example, so one will take that there is about on the top 20 plus 160 plus 10 plus 10 watts, that is total of 200 watts is dissipated to an air that is flowing at 21 CFM, which is equivalent to some mass flow rate of roughly 0.0116 kilogram per second. And this is the bottom side of the structure. So, the heat source is here. So, the heat source on the bottom side is abridged to a copper plate through a thermal interface material, and then it spreads over a larger copper plate, and from here there is another plate, and then heat sink is mounted where air is flowing. So, one has to account for the TIM resistance, one has to account for the spreading resistance from a smaller heat source to a larger copper plate. Then one has to account for the bulk copper conductivity, and then one has to again account for the base thermal conductivity of the heat sink, which is this base, and then the heat sink itself, the convective resistance of the heat sink itself needs to be accounted for. All the required information to calculate all these things are given in the problem statement. So, if one calculates RTIM, then is about 1.44 degrees C per watt, and if one calculates the spreading resistance, it is about 0.056 degrees C per watt. If one calculates the copper resistance, it turns out to be 9 degrees C per watt using L by Ka, L being the length, which is 150 mm, thermal conductivity is 400, and the cross sectional area needs to be accounted for. And then the heat sink resistance is estimated to be 2.1 C per watt. Overall, if you sum all these resistances, and I missed out the base thermal conductivity resistance, which happens to be 0.76 degrees C per watt. So, overall, if you sum all these resistance, because all these resistance are in series, there is no parallel resistor, assuming that the PCB is a perfect insulator, because otherwise there may be some heat flowing from the top larger power processor that is sitting on the top to the bottom heat source, but we ignore that for sake of calculation. We get total sum of 11.36 degrees C per watt. So, writing the resistance R sum as Tj minus T ambient, the local ambient, which we calculated using the top side heat divided by the power of the low power device on the bottom side. Using this relationship, we can calculate T junction to be 209.8 degrees Celsius. So, one sees that the copper has very high thermal resistance, even though copper has high thermal conductivity, because it has to carry over 150 mm of length, that this becomes a extremely challenging task. And if one tests all these heat pipe thermal resistance, if it is a sintered wick, then their overall heat pipe resistance turns out to be in the range of 0.1 to 0.4 degree C per watt, and in this case we pick a value of R of the heat pipe equal to 0.1 degree C as a simple estimation. That is the problem, that is, it is a very high performing heat pipes, and they give you a resistance of 0.1 degree C per watt over a distance of 150 mm. We use that, and if we replace copper with this, then because this resistance is much smaller now, if we go calculate a junction temperature with heat pipe, then it turns out to be 94.3 degrees Celsius, which is well below what is needed for cooling these things. So, in this example, that is why heat pipe is, even though we did not substantiate these numbers, but these are typical numbers provided by manufacturers or tested values as well, and they are in this range. And so, using a value of 0.1 degree Celsius per watt as a best case scenario, you get a resistance or a junction temperature of 94.3, which is almost close to much less than 110 degrees Celsius compared to the copper based solution. And also on top of copper being poor in terms of thermal conductivity, poor in terms of performance, weight is also much higher for copper, and compared to heat pipe, which are hollow metal pipes, and they have only very thin wall material with sintered wick. So with this, we will conclude that heat pipes are quite effective in carrying heat from location A to B, and also with this example, solved example, we will conclude this module. We will conclude the discussion, not the module, but the discussion on thermal design of electronic equipment with reference to convective heat transfer.
Good morning. I am just here to give a closure to what has been about 70 odd modules that we have recorded for our course on convective heat transfer fundamentals and applications. My thanks to Professor S.V. Prabhu and Professor Shankar Krishnan of IIT Bombay for participating in this effort wholeheartedly despite their busy schedule. Hopefully, we have encapsulated fundamentals as well as some amount of applications about from this wonderful topic. The focus primarily has been convective heat transfer fundamentals, and about 20% of the course has been on applications, 20-25% of the course has been on special topics or applications. Just to put things in perspective, I will take about 5 minutes of the time to run over what has been done, so that you can see the connect between what topics we have covered and how they are linked to each other, and hopefully you will go back with a better understanding of fluid mechanics and convective heat transfer. We started off with classification of convective heat transfer. So that was something which all of us have done in undergraduate curriculum, and various aspects were covered here. Then we went on to derive the Reynolds transport theorem. This was something which most people do not cover in undergraduate curriculum, but this being a course which mostly faculty members would be taking, and also students, we have covered this Reynolds transport theorem so that it forms the basis of the derivation of the conservation equations. From this, we went on to derive conservation of mass, momentum, linear momentum, and energy equations. And Professor Prabhu went on to show or discuss relationship between stress and strain, which was going to be used in the momentum equation also. Relationship. This is again not covered in undergrad curriculum. This went on to be used here. Then a lot of time was spent in talking about scaling analysis for boundary layer of boundary layer equations. So boundary layers form one of the most important topics in fluid mechanics and heat transfer, and sufficient amount of time in this course was spent on trying to solve the boundary layer equation. So we started off first with scaling analysis. Non-dimensionalization of the governing equations were done after they were derived. Then it was shown that Cfx is a function of Re, and Nusselt number is going to be a function of Re and Pr for force convection. And there was also introduction to other non-dimensional numbers like Eckert number, which was important in high speed flows. After doing that, scaling analysis was done, where boundary layer equations were reduced from the Navier-Stokes equation to simplified equations so that they can be solved. After the boundary layer equations were scaled down, basically we introduced u of the order of u infinity, x is like this, y is of the order of delta, and then v was coming out to be of the order of u infinity delta by L, and based on these certain terms dropped off very conveniently because they were much smaller compared to the other terms. Okay, after these were scaled, relationships were derived for Nusselt number for small Prandtl number, for large Prandtl number cases, and this actually I would say was one of the highlights of what we tried to show you. We obtained expressions where we got something like this. Nusselt number is of the order Re to the power n, Pr to the power n, and this came directly from scaling analysis. And what we said was, any correlation that you have for laminar flow for Prandtl number less than 1 or greater than 1 or even equal to 1 will have a particular value of m and n unique to that particular case. So, Pr less than 1 would have one specific m comma n, Pr greater than 1 would have another m comma n, and all correlations that you would see that would be derived for these conditions would have the same m and n, and what would be different is this coefficient in front of it, which scaling analysis would not give, but this would be obtained from integral method or similarity analysis. So, this was the highlight of something which we have. So, most important thing from undergrad curriculum point of view, there are a bunch of correlations that are given in textbooks. If you classify them for laminar flow Prandtl number less than 1, you would see the indices to be identical. If you classify them for Prandtl number greater than 1, that category of correlations for flow over a flat plate would have the same m and n. What would be different is the coefficient which people would have got from different experiments or similarity method or integral method. So, these three arrows would be how you get the coefficients. M and n would magically come out to be the same. Then we went on, we spent sufficient time on similarity method. We said how similarity method is a very accurate method, but a very restrictive method because the condition required for similarity are reasonably strict, in that the similarity variable should only be there, no more x and y, no more other independent variables. The governing equation coefficients that you have in front of the terms as well as the boundary conditions should either be functions of the similarity variable alone or should be constants, and that basically is very restrictive. So, you can solve a few problems using similarity method. A class of problems that we derived equation for was the wedge flow problem, and we considered a suction or blowing velocity and pressure gradient parameter m was considered, and we derived the equation for both cases where pressure gradient parameter m was equal to 0, less than 0 or greater than 0, Vw positive or negative or equal to 0. And then after deriving the equation, we went on to do it for a flat plate with no pressure gradient. So, similarity method was done for flat plate with no pressure gradient, that means m is equal to 0 and no suction or blowing Vw equal to 0. This gave us Blasius like equation, and this was solved, or the solution was presented for getting the boundary layer thickness and coefficient of friction. Similar thing was done for the energy equation, where we said that you can have Tw as a function of x and viscous dissipation is not equal to 0. Equation was derived. And then we solved it for constant Tw and viscous dissipation equal to 0. We said that if these are there, then the similarity variable has a particular set of numbers that it can take, so on and so forth. And then we explained the concept of Reynolds analogy. Once these solutions were obtained, we just talked a bit about Reynolds analogy, which was covered in the derivation stage itself. Okay. Then we went on to integral method, where we integrated the momentum and energy equation. So, integrated momentum equation and integrated energy equation, we took the general boundary layer equations and integrated it, and then we simplified it for flat plate. Used profiles. So, used profiles with u by u infinity is a plus b eta plus c eta squared plus d eta cubed, and also temperature profile T minus T infinity by T wall minus T infinity is similar form. We got from this displacement thickness or d star, momentum thickness, enthalpy thickness. From this we got Cfx, from this we got Stanton number. Okay. So, these gave us coefficients for Cfx expression and Nusselt number expression, which were also compared with scaling analysis. The powers were identical. Similarity method also gave us coefficients for Nusselt number, which were again compared with similarity analysis. Okay. So, after doing this I think we covered up till I think module number 28 or something. Then Professor Prabhu introduced turbulence in detail. We spent sufficient amount of time in Reynolds averaging, then universal velocity profile, friction factor for smooth and rough pipe, so on and so forth. About 7 to 8 modules on turbulence was delivered, and this we do not teach at an undergraduate level so much, but this would give students an appreciation of the complexity of the problems that would be there in real life. Then we went on to natural convection. Natural convection, professor derived the governing equations. Then scaling was done. This was something which is very new for natural convection. Scaling analysis was done and special cases were studied. After having done this, kind of the course in terms of its content is done, except that we went on to study a case of, we went on to study internal flow. I forgot about it. Internal flow, we did the derivation of velocity profile, then looked at energy equation simplification, solution for constant wall heat flux and constant wall temperature case, concept of fully developed flow and thermally fully developed. These two concepts were widely used here. Then we went on to show the temperature distribution in the entrance length like this. This is QW equal to constant T versus X, and this would be T versus X for T wall equal to constant. Went on to show UA, which is overall heat transfer coefficient, which is associated for this case. Solve the energy equation for laminar flow, derived Nusselt number equal to 4.36. Showed that Nusselt number here is going to be 3.66. Established the concept of hydraulic diameter and presented results for Nusselt number for other geometries. Then very quickly we considered effect of viscous dissipation, introduced the concept of Brinkman number, this so that we understand how Nusselt number changes because of viscous dissipation. With this, the convective heat transfer fundamentals topics were completed. Then few lectures were given on condensation. Nusselt's condensation was studied, laminar condensation, and correlation for H was derived. Few lectures on boiling were studied. We went on to show the boiling curve, single phase natural convection, nucleate boiling, went on to define terms like CHF, minimum film boiling temperature, classified segregated the boiling curve into various regimes: film boiling, saturated boiling, and nucleate boiling. Talked a little about what CHF could mean, went on to say that CHF is caused by departure from nucleate boiling or dry out, which are both different. Also said how a very important concept called void fraction needs to be there in two-phase flow, which is very different from single phase, and because of the flow patterns or flow regimes being different for the same m dot f and m dot g, depending on the orientation, we get different flow patterns, and therefore we have a different heat transfer and hydrodynamic characteristics in case of two-phase flow, which is what makes it very complex. About 5 lectures were given on boiling, and this was something which is like an introduction that you can give to your undergrad students. Then Professor Shankar came and talked about application for electronic cooling, fundamentals, what are the criteria that needs to be established, which needs to be taken into account for designing, and then 1 or 2 cases or examples were studied. So this has taken us a journey about 72 or 71 modules, which is about 35 to 36 hours of lecture, and through this we have tried to give the students as well as our faculty colleagues an overview of what is the broad field of convective heat transfer. This is by no means complete. This is what a faculty member, if he or she is able to appreciate while going to class at an undergraduate level, he definitely would be able to communicate things far better. And the idea has been that most of the time in undergraduate curriculum, correlations are given to students and they are asked to memorize it, which is absolutely incorrect way of handling things, because it's not something which needs to be memorized. Correlations can be given in an exam and students can be asked to use it. In fact, at the exam stage, the problems could be where you are going to do energy balance, come up with a differential equation, so on and so forth, where the real test in terms of the understanding is seen. Problems are necessary, numerical problems are very important, but it should not be such that they are only memory based thing, where you have the right formula, the student gets full marks. It's not that. A correlation, multiple correlations can be used for the same problem. They might only differ by 10 or 20% in their answer. It is not incorrect. The idea being a correlation has been derived for a particular flow situation using a particular geometry, particular set of experiments. Somebody else over the years may have done a similar experiment and a better or newer correlation may have been there for the same kind of situation. Doesn't mean the older one is incorrect. So we should not give so much importance to the fact that a number, a Nusselt number is right to 2 or 3 places of decimal. If a Nusselt number comes out to be 164 and somebody gets about 158 or 172 or something like that, it is as correct as the original number, because every correlation that is being derived or that is being generated has a certain level of uncertainty associated with the experimental data and also with the coefficient and the exponents that are there in the correlation. So as faculty members, we should not give so much importance at an academic level for the correctness of the numerical answer, by which I mean the heat transfer coefficient is coming out to be 21.45 watt per meter squared Kelvin. Doesn't matter if it is 20 or 23. As long as the concept is correct, the student has understood the concept and put in the right equation, right terms are there in the formulation and the solution, the credit should be given to the student. Numerical answers in convective heat transfer matter only so much, especially at an undergraduate level where you're not designing anything. Ultimately, in real life designs, heat exchangers or something, there are so many empirical factors which are there, and ultimately factor of safety is there in engineering, which will take care of the design. So you might derive something with a certain thickness, or pressure vessel can be obtained from design to have a particular thickness, but when it is manufactured, it is going to be of a much larger thickness because of factor of safety. So engineering takes care of the fact that we have correlations and empiricity in our formulae. Therefore, as teachers, we should not be overly critical about numbers. We should not be so bothered about correctness of numbers. Correctness of procedure and concepts is what is important. Through this course, we have tried to give you an overview of convective heat transfer, a little from the postgraduate curriculum point of view. Hopefully, it will be useful when it is taught to undergraduate students, as well as for teachers for greater, when they go to read technical documents, etc. It might be easier, might be of great help to them. If there are any suggestions which you want to give, if there are anything which you felt is incorrect, you want to communicate to us, please feel free to do so. Our email addresses are there in the web page, IIT Bombay Mechanical Engineering Department web page. You can drop us an email with specific queries, with specific comments, and of course point out flaws or give suggestions for improvement, so that if something we are going to do next time for another course or something like that, we would definitely try to incorporate the same. Thank you very much. Best wishes.